Okay, so now we can kind of get to the meat of the discussion here, and we can actually see how this theta notation might help us do a little bit of analyzing in an algorithm. We have to remember that analysis of algorithms, it gets really complex really quickly. The more complex the algorithm is, the more complex it is to do an analysis on it. So we're going to look at just a couple of lines of pseudocode and see how the theta notation can be applied, but I think at least that'll give us a taste of what's going on, at least hopefully. So you can see the instructions at the top are to find theta notation for the number of times that the statement x equals x plus 1 is executed. And so the idea is that, keeping this very simple, the input into this algorithm would be n. Right? So we want to find a function of n. Right? We want to find some function of n. That's what we've got to do first. Find some function of n that represents the number of times that this statement is executed, and then we're going to apply what we learned about theta notation, find the theta notation for that function. Okay, so we talked about how we can trace through for loops, or you've maybe read about that or already know how to do it. So I'm going to look at this a couple of different ways. Actually, I'm going to erase this, because then you might need that space down there. If we try to make a table, we can certainly do that. Now what we've got is a nested loop. We've got a for loop within a for loop. And here's how that works. I'm going to set up my table. I'm going to track I and j, and then I'm just going to come in here, and when the statement x equals x plus 1 is executed, I'm just going to put a check in there whenever I think that gets executed, just to help me count the number of times. This statement really doesn't mean anything. It's just whatever's in there, we're going to count how many times that executes. Okay, so here's how the nested loop works. First, I get set to 1. Right? And then we go down and we run the next loop. So when I is set to 1, this loop's going to run for j going from 1 to n. Right? And then we're going to go back here. I is going to get set to 2, and then we're going to come in and j is going to run from 1 to n again. So the way it works is this. I gets set to 1, and then j comes in and loops through down to n. Now this statement is in the loop j, so it's going to get executed each one of these times. Right, and then we're going to kick back to the top, increment I by 1, so I would go up to 2, right, and then we kick down to the loop for j, and that's going to run down to n again. So it's going to execute the statement here, here, here. And of course, that's going to continue. It's going to continue until it runs for the last time on this outer loop, which stops at n. So this would continue until we get down to n. Right? And once we got to n, this j loop would run one more time down to n. So it would execute here and here. Right, so we could count. Here I executed the statement n times, right? That was n times. Here I executed the statement n times. So I did that once, twice, and then I would do it until I got down here. I would execute n times. Right? So I executed n times on the j loop for each of the times that I incremented, which is also n, right? The I loop incremented n times. And so you can see that for each of these n times, You see that for each of these n times, the j executed n times. So our function would simply be n squared. Now let me provide a little bit more mathematical way that we might have gone about figuring that out. Remember, we learned about the sigma notation, right? Since this goes from 1 to n, and j also goes from 1 to n, one way we might think about doing this is just with a nested summation. We're going to take I from 1 to n, and inside of that we take j from 1 to n. And again, we're not going to put x equals x plus 1 in there. Let's just put a 1 in there, because, and the reason I put a 1 is because I just want to count one time for each time that I increment, really is what we're doing. We just counted one time for each time that we incremented. Okay, well, what would this look like? Sum as I goes from 1 to n. Now if I just have a constant in there, what that means is add that 1, starting at 1, going to 2, going to 3, until you get up to n. So in other words, just add that number n times. Oops, I'm sorry. That should be 1. We just add that number n times. So if I have 1 added n times, that just adds up to n. N times. Right, so that gives me the sum as I goes from 1 to n of n. Right, and again in here, this is just a constant. There is no I showing up. This is just a constant. So that means add n times. So this would be n plus n plus, right, we just add that n times. So if I add n times, that's equivalent to saying take n times n, which gives us the same thing, n squared. Right, now ultimately, remember what we wanted to do. We've found a function in terms of the input size of our algorithm. It tells us if we have an input size of n, then the number of times that that statement gets executed is n squared. And we can find the theta notation, because this is just a simple polynomial. Remember, all we have to do is look at the degree of our polynomial, and we know that the degree of the polynomial is n squared. So we know that our function has theta notation n squared. I mean, this is the simplest second degree polynomial that we can have. Right, way back up here in our first example, we had a second degree polynomial, ended up being order n squared. Theta notation of n squared. Right, so of course, if we have just the polynomial n squared, it's going to be theta notation of n squared. Okay, so that's how we might take a few lines of code and analyze them. What I'm going to do is I'm going to do one more example and then try to sum all of this up. Hopefully it'll make a little bit more sense. I'll do my last example in another video.